Great, let's go ahead with the next talk. So this is Ariel Bensimon, who is, was until recently a PhD student in the group, in the Aebersold group in Zurich, now graduated, and he spent most of his time during his PhD looking at SRM analysis of phosphopeptides. And so he's going to tell us a little bit how translating this works into the DIA space. So Ariel, please.
So throughout the lectures during this week, you've been hearing a lot about PTMs. In this lecture, I'm going to be focusing on phosphorylations as an example of a PTM. These were mentioned in different lectures, and I'll try to take a step back and walk you through the different steps that will help you to analyze, for example, phosphorylations in your data set. Some examples will be from SRM, and some examples will be to highlight the opportunities and challenges in analyzing PTMs in DIA SWATH data. So, of course, this talk is not going to be about the first part, so how you enrich phosphopeptides or the preparation of the samples can be equivalent for any type of acquisition. We're going to start from looking at the point where we've acquired the data. And the most common problem that we need to think about when we're looking at PTMs is we don't only deal with the identification of the protein, but we also need to deal with the identification of the site. So we would like to assign correctly the site where the modification occurs on the sequence. In a case like this, as phosphorylations, then we usually consider three options: serine, threonine, and tyrosine, and there could be several of those in a certain peptide sequence. Most commonly, this is done using shotgun proteomics or discovery proteomics, where we follow three steps. Very generally speaking, we do our DDA runs, we do a database search that gives us a list of identified phosphorylations, and then we use some sort of tool to do MS1 quantification. And the result of that is usually a certain matrix, which gives us quantitative values for certain phosphorylation sites or phosphopeptides, depending on the tool that you're using, and it tends to be with a lot of missing values. How many people here have run a phosphoproteome experiment? So most of you, great. People are usually doing it with DDA? Most of you. So you are probably familiar with these types of heat maps. And of course, there are ways to impute the data. There are ways to deal with these missing values. One of the ways is also to acquire the data differently and try to look at it from a different perspective. The problem of missing values has here to do with two things. One is that we get multiple site assignments. So from the search results, we get the same precursor, the same, let's say, singly phosphorylated peptide, but at different assigned site. And then the second problem is that this is carried over into the alignment that is based on MS1. So it's the same precursor, and then the tool needs to decide whether this is assigned to this sequence or assigned to that sequence. To just illustrate this problem, this would be, for example, a certain protein, a yeast protein, different phosphorylations, singly phosphorylated, doubly phosphorylated, perhaps miscleaved, and there are several identifications per sequence. And then when we look at this matrix, there could be some of these could be missing values, and these could be also true missing values. So one option is that there's an error there was some error in the alignment. So sometimes two localizations were assigned to two different peaks at the MS1 level, and sometimes they're aligned to the both peak, and there's a missing value for one of them, and so on and so on. So there's not a very clear way to match the number of phosphosite IDs in shotgun to the number of peaks that we will see by the chromatography, and make sure that this is done correctly across large data sets and many, many runs. In recent years, there have been tools that have been developed to look at the DDA spectra and try to correctly assign, so to try to also assign the probability, or at least estimate the localization probability, such that we do not only get a probability for identification, but also a probability for the site assignment. But what is very important to note here is that you can choose if you want to use these things, but whatever at the end of the day will pass all your cutoffs, whether it's a peptide probability or a causation probability, all of these things will come into our DDA searches. And as we've done in this course, we use these DDA searches with any type of probabilities in order to build our libraries. That means that all of these identifications will make it into our libraries whenever we want to afterwards go and extract them from DIA SWATH type of data. So this is a very important thing to note, and we'll see towards the end of this talk how to deal with this problem. First, I'd like to introduce a term that was mentioned already this morning. Whenever I'm going to refer to a certain precursor that has the same mass, so this is a singly phosphorylated protein with the same sequence, but has different possible localizations, I'm going to call it either a phosphopeptide isomer, and sometimes I will call it a peptidoform. So in the case of dealing with DIA runs, we would have this certain sequence, for example, in our libraries, and then eventually what we would like to do is run the MS quantification. There are two things that we would need to consider along the way in order to be able to do that correctly, and that is look carefully at the transitions that we've chosen in order to extract the peaks, and look carefully at the retention time. And I'd like to explain these 2 points now. So far what we've done was, for example, in the tutorials, we did the top 6. So we selected the 6 most intense transitions so that we can get the best sensitivities in extracting our peaks. And then we took 6 or 8 or 10 number of transitions in order to gain selectivity so that we can extract what we think is the correct peak. These were all unmodified peptides. When we look at modified peptides, we would need to consider also other transitions that will help us to localize the modification. In this case, they may also be not very abundant transitions, they may be not very high, but they will give us selectivity in terms of site assignment, and we need to pay attention to those as well. So the option of just choosing the top end might not be applicable in this case. Just to give you, to illustrate this by an example, these are the 3 sequences that we mentioned before, and then some of the ions are, for example, unique only to this localization of the site. So we might want to extract those in order to be able to term whether this is a correct site. For this site, there are several ions that are unique to the others. And of course, there are also cases when there isn't a specific ion. So, for example, for this localization, probably all the ions are shared. This, for example, is an ion that is shared, and there are many other examples, but we can try and look at combinations of ions. For example, if we would like to localize these ions are shared with this possible localization, this ion is shared with this possible localization, but if we were to detect a peak that has the combination of all 3, this would potentially indicate that we're looking at this localization as opposed to this one or this one. There are also other explanations that we will look into in a moment. So the first point that I wanted here to make is that in addition to those transitions that we select for detecting our peaks, where we want to select the most intense ones, we usually also pay attention to these unique ion signatures. These combinations could be a single, could be a set of ions that will try to best describe the correct phosphosite assignment. The second thing that I would like to highlight here is the use of neutral losses. This is something that can also happen very quickly if we're just going to select the top n transitions. This is just an example of one spectra, and some of the most abundant transitions fragments that we have in phosphopeptide specters are the neutral losses, so these ions that have lost the phosphor groups and the water. So these would be selected into our top 6 transition, for example, but these are, while these can be very useful for quantification, they are going to be very hard to use for the identification of the site. And the reason is the following. If we have, for example, a phosphoserine in it, there's a neutral loss, we will get the dihydroalanine, but the same thing can occur when just a serine would lose water, we would get to the same mass. So, for example, if we would like to localize, again, on this sequence, a certain phosphorylation, we think it was here, we would take the neutral loss, we would get to this transition, but if the phosphorylation occurred on a different residue and this serine lost a group of water instead of the phosphor group, we would still get to this transition. So these transitions that carry neutral losses are very useful, but not for the purposes of site assignment. So whenever we select them, we should be aware of how we're going to use them and be aware what makes it into our library. So of course, all of these parameters can, of course, be defined either in Skyline or whatever tool you're using, and of course, in the parameters of the search. You just need to be aware of them when you're selecting the transitions. The second point that I would like to highlight is related to retention time. Sorry. We've talked a lot, mentioned a lot the retention time calculators and the possibility to do retention time alignment. And at the end of the day, the retention time of a peptide depends on its properties, the chemical properties, and of course, the sample background, the quality of the chromatography, etc., etc. There is a possibility to make use of that chromatography settings work them in your favor when you're working on modified peptides. That is not always the case, but in some cases, the fact that the phosphor group is localized on a different residue will also impact the way that it is eluted from the chromatography. So, of course, depending on the peak resolution, in some cases we would have two different modifications that elute as one peak under the chromatography, and in some cases, two different site assignments would elute as two different peaks. In these cases, we have, in addition to the transition information, we also have the information that is related to retention time. These changes may not be very big, but they are very reproducible, so we can try and take these into account. To illustrate this with an example, so let's say we're looking at a certain phosphorylation sequence, and it could be phosphorylated on one of these three residues. We could, for example, measure each one. If we had measured each of these ones separately, we would figure out the retention time, and then what could happen is the following. In some cases, these different possible localizations are separable in retention time, so we would get, for example, serine, the possible localization on serine 4 would give us one peak at time x, and then two localizations might only partially coelute, but then we would be using these unique transitions in order to separate them. So we would use this transition for serine 6 and this transition for serine 8. There are also cases where this does not happen and all the phosphopeptides coelute. In this case, we cannot use their retention time. They all have x as their certain retention time. And we can try sometimes to use these unique transitions for quantification, but we will not have this leverage of retention time. I'll give you a couple of examples. These are examples from SRM data first. So in SRM, we measured 3 different localizations on a certain phosphopeptide from yeast, the one that I showed you before, and you will notice that the retention times are slightly different. When we mix all of them together, we get these as 3 eluting peaks. This is data that was collected by Tina Ludwig that you met at the beginning of the week. And the relationship between these 3 peaks is conserved throughout every measurement. So what we get here is 3 possible localizations that are separable in retention times. These were synthetic peptides, so the localization was known in advance. And now we can, of course, spike them in our samples and then do a very accurate quantification of a light to heavy ratio. So to be sure that we're quantifying the site that we're interested using these heavy peptides. I'm not sure if you saw in the course, was there light to heavy? No. So if you would have light to heavy in Skyline, then what you would have in the blue is the synthetic, in this case, whatever is defined as the heavy modification, that is in blue, what we spiked in. And in red, you would have the endogenous. And in this case, what we can say is that this localization, we can calculate for it a certain ratio. For this localization, we can calculate a certain ratio. And this localization either does not exist, and this was a mistake from the search engine, or it exists, but below the limit of detectability. We cannot distinguish. But this also, of course, gives us a handle that we were able, using these synthetic peptides, to localize correctly. Let's look at another example that is more complicated. So in this case, Tina had 5 different peptides. Each of them were individually measured. And when all of them were mixed together, well, now it gets a bit trickier. So now trying to separate each one of them by retention time or by transition might not be so simple, and certainly some of them coelute. And in this case, not all of them are separable, some might be, so we might be able to pick some transitions for serine 27 to separate it from 24. But for example, separating 24 and 25 will clearly be very difficult. What we can do in such a case is either adjust our chromatography. So maybe we would change something in the parameters, the type of the beads that we use, the graded, etc., to increase our peak resolution. And in doing so, we would be able to get some separation. My guess in this case is that it might not work. And the other thing that we might do is look at specific transitions. So we can go back to the data. In this case, this was done in advance because this was SRM data, but in the case of DA, we can go back to the data, select other transitions, these unique ion signatures, and extract those specific ions that would well distinguish between certain localizations. So for example, if we had extracted Y5, this would separate for us serine 24 and 25. We would get a certain quantity based on a single transition, but it would be able to give us some piece of information about the difference between serine 24 and serine 25 if this is something that we were specifically hunting for. Of course, all of these two examples that I just gave you were done by SRM, but the same carries over to DIA SWATH. So in this case, I took two different synthetic peptides for a protein called MCM2, and these are the two possible localizations. And also, of course, this does not have anything to do with the acquisition, but on this chromatographic setup, again, these two peptides would be separable, and I would extract here the Y4 in order to distinguish between this mass and be able to localize. So in this case, we could determine that the endogenous phosphorylation is carried on this serine, and we could not find any signal for the endogenous phosphorylation on this serine, and by using the retention time information and the specific transitions, we were able to determine what is the correct site assignment. What made it very, very easy in this case is the fact that we had synthetic reference peptides. So we had a ground truth, we added it into the sample, and simply looked for the coelution between the endogenous and the reference. This creates one complication, which is the fact that we can no longer use the B ions, because the B ions are going to be shared between the light and the heavy. So we're losing some ions that might be very abundant in our spectrum. We will no longer be able to use them for quantification or identification because we're acquiring here in the IR swath. And given the windows that we use, it's very likely that they will be in the same window. Is that point clear to everyone? Okay. Unfortunately, in most cases, we don't have synthetic peptides. Actually, when we're doing in most of the DIA swath types of experiments, if we're interested in entire phosphoproteome, then we don't have it all synthesized. So we're likely to be working in the label-free sphere of quantification. And then the workflow that we've been doing so far is we had some spectra that came from some source. We built a spectral library. We selected transitions based on that spectral library. We've just brought to our attention that we should also take into account what type of transitions include those unique ion signatures and extracted a certain peak, for example, using Skyline. How many people think this is the right peak? I see one. Dot p-value is quite low. That is correct. In all the examples that I will show you, the dot p-value is quite low, so that you don't have any tools to compare. There's also no scoring model here. Just look at the peak. I would say there's quite a few transitions here that coalute, and they looks like a very nice peak. My first guess would be, yeah, maybe. However, whenever we're looking at such a peak, what we did so far in the course, we were looking at unmodified peaks, and we asked the question, is this the correct peak? So can we detect the peak, and then can we correctly identify it? And we used different sets of scores, all of them which I'm trying to hide today, except the dot product, which is still shown on the print screens. And then the second question that we want to add here is this the correct site assignment? So these are two independent questions, and we're going to try and look at some examples in order to highlight some of the challenges and some of the opportunities that we have whenever we're doing DIA swath, because in some cases it's going to get more difficult, but then we also have some other opportunities. So I'm assuming here that we acquire the data in some sort of wide window, and I'm assuming that we're working in a workflow that does targeted extraction. And in fact, the peak that I just shown you is this peak, and next to it, there's actually a much higher peak in which, when we look at the MS1, we also have a much higher MS1 intensity. Our library had two different localizations. So perhaps these are two different phosphosites. Maybe these are two different site assignments. That could be. We could look at the transitions and try and look at each one of them. The first thing that I would do is look at the MS1. As you've done, I guess, a couple of times by now in Skyline, we click on that little circle, and we see that here we're actually extracting probably something else, but not an ion that we would expect, whereas here we're really extracting the peak, the monoisotopic group that we think we are extracting. So in this case, we had 2 peaks. These were not 2 site assignments. This is probably something else. We will in a moment look at different options of what this could be, but it is not 2 different site assignments. We had 2 site assignments, but this is either a different modification or something else that is going on, but not a localization problem. And this is where the challenge comes. Since we're acquiring in wide windows, we are co-fragmenting things that have very different masses, but then extracting them, and we need to take into account other pieces of information in order to be able to determine whether this peak that looks pretty nice in terms of coelution of a lot of transitions, there's probably 10 or 12 transitions here, is really the right peak.
So, can you go back? So how do you explain, I mean, it looks like there's something coeluting over every one of them, but they always look like the MS1 extracted chromatogram is less intense than the fragment ions. So those are all tens of thousands of fragment ions and only thousands of precursors. Mm-hmm. How do you explain that?
I actually don't know. Do you know? This is from the 6600.
It might be something to do with the centroiding, right? Because the MS1 is collected at 30,000 dissolving power, and the MS2 is collected at 15,000 dissolving power. So maybe the centroid is behaving differently on those,
or the extraction windows are different widths or something.
Well,
yeah. Okay.
Too, but yeah. Is it centroided data or?
No, it looks like profile.
No, this is profile.
But anyway, it's something to look at, I guess.
So I almost always see, I will show one example where it's not the case, but I actually don't know the answer to that. Okay, so in this case, I gave you an example where we just without any scores, we look at the data, we had 2 identifications in the library, but 2 different peaks that have very different explanations. In another case, now the ratios between the MS1 and MS2 look very different. At least at the level of the MS1, it seems like we extracted the right monoisotopic peak. Perhaps we have a case of 2 different site assignments, and perhaps there's another explanation here, as I'll show you in a moment. But this would make us a bit more inclined to say we had 2 library IDs, we also had 2 peaks. Perhaps there is an issue of site assignment here. Not always the case. Sometimes we have 2 peaks. We have, as I've shown you before, also 2 peaks at the MS2. In this case, we extracted the monoisotopic peak, and in this case, we extracted something else. Perhaps it's an amidation. So this peptide was modified by another modification, acquired, of course, within the same window, because this is a 1 Dalton shift. We had 2 identifications in our library, but only one of the peaks corresponds to the mass, and the other peaks corresponds to another mass. So we have this constant, I don't want to use the term convoluted, but relationship between different combinations of modifications plus the problem of site assignment. This is, of course, related to the size of the window that we acquired. But in a case like this, when there's a 1 Dalton shift, we're probably not going to be able to solve that without any additional scores that relate to the MS1. So if we were to score the MS1, of course, this would pop up, but I switched off all the scores in this case. Another thing that can happen very often, here, for example, I've extracted a peak for this sequence, modified here, and then I went to the data and extracted also the oxidated form of this peak, and without doing anything, it gave me the exact same peak, going to the same retention time. There was actually no, actually there was somewhere over here an oxidized form of this peptide. This was the most intense peak, and this was selected because a lot of the transitions between the oxidized and phosphorylated and just phosphorylated, they will share a lot of the transitions. These 2 transitions will point to the same place, to the same peak in retention time, but of course will have a very different MS1 level score. And of course, if we would interrogate this a bit more deeply, we would immediately recognize that there's something going on wrong. So when we're looking at modified peptides, and we always need to account what could be the other explanations. This, of course, applies to any type of extraction. And we're accounting for these possibilities by using a variety of scores. In this case, we had 2 library IDs for two different types of peptidoforms, one with an oxidation and one without, a first iteration extracted the same peak, and this would be resolved by scoring. So these are cases where we have two peaks or two library IDs. We also get one or two peaks, and there are different explanations. And the opposite also occurs. So we have two library IDs. In this case, the difference is the site assignment, and both of them point to the same peak. So now there are two options. One, two phosphorylated peptides with a different site are coeluting, and that's why we get one peak. Or there is one phosphorylation, only one correct site assignment, and the other is a false site assignment from our library. How would we check that? So I didn't hear. Unique transitions, correct. So what for example, would be a unique transitions that would distinguish these two? Y4. Why, you said Y4 and Y7. Why not Y7? So Y7 would not distinguish between the two because Y7 would be of the same mass between the two. Y4 would distinguish between the two, and indeed, that's what I did. So I went back to the data, extracted the Y4 for each one of these localizations. At least for this localization, the Y4 is pretty high, so we're kind of lucky we have some more evidence to support that this is the correct localization. This is evidence to support the localization because there's also the possibility that this is also a site that is assigned there, and simply Y4 is not a very abundant ion, so we cannot exclude that option. But in this case, I would say there's more evidence for this localization rather than this localization. This was a case, an example with two, and of course, as you've seen already in phosphodata, you don't always have two localizations, and so far I've only shown you examples with one phosphorylation site. So let's take an example with three. Again, deciding on which is the correct ion to resolve these three possible localizations is going to be more difficult. But in this case, we can, of course, extract as many ions as we want, and we can also look at combinations of ions. For example, here I extracted the whole series, basically from here, 987654, and between these 987654, I can then try and look how much evidence I have for each localization. So for this localization, for these set of masses, I would have 6 ions that are coeluting. For this localization, I would have 4 ions that are coeluting. Here we have 3, I would say, and maybe I would now deem this localization to be most probable, again, assuming that this P corresponds only to one real phosphosite, and this is not the case of a case of coelution where two different sites coelute together in one peak. Then I would need to look at perhaps other ions and see maybe I can resolve it, but in this case I would say there is more evidence leaning towards this site localization. So I hope that with these few examples, I could show you that site assignment is a bit of a complicated problem. How would we go about it when we have a very big data set? So here I cherry-picked for you a few examples. We looked, we scrolled out, we looked at a couple of retention times, but now in a very big DIA SWATH data set, this is not going to be very realistic. So I bring up these points. Of course, we would have a lot of scores that could help us here, but only to highlight some of the challenges that we might have with site localizations. Does anybody see here also an opportunity? How could we use this? So one option, for example, would be, if we go back to this example, is to take transitions that are shared between the two, try to extract a phosphorylated peptide, but also with these same transitions, try to extract an oxidated phosphorylated peptide. So by the fact that we have these wide acquisitions, this is not just only causing us problems in terms of scoring, but also enabling us to try and extract peptides that maybe were not in our library using some common transitions as a starting point, and then trying to refine based on these common transitions and trying to resolve retention time information, which is the correct peptidoform in terms of site, in terms of mass. So this is not just a problem, but also an opportunity for you. But in order to speed things up and make it a bit more feasible, George Rosenberger, he's also a graduated PhD student in our lab, wrote a tool, an algorithm called Inference of PeptidoForms that automatically does the steps that I've just described to you now. So the first step that we did was to try and detect a certain peak group and then make sure that we have the right precursor group. So basically, the thing that we were doing was to look whether we see a nice peak and then to say whether this is the right MS1, and does that give us more of a probability that this is the correct peptidoform, at least in terms of precursor. And then the second thing that we did was to try and take more transitions in order to be able to identify. So first we calculated some sort of probability that this is the right peak. We said it looks correct, it looks like it has the correct MS1, 6 of the transitions that we had in the library correlated, etc., etc. So maybe candidate 1 will have a higher probability than candidate 2, for let's say we had 2 in the library. And then in the second step, we added these transitions, and for each one of these transitions, we could extract B2 and Y3, for example. These are just artificial examples here. Try to extract them, and then rescore and say, do they all coalute together? And this will help us in the identification of the correct peptidoform. So to try and say whether this is the right precursor, the right peak group, the right set of modifications, the right mass, and of course, whether the site is correct. All of this is integrated together in a tool that George wrote, and it goes through the entire data set by trying to assign certain probabilities to the precursors and the peak groups, and then taking out these unique ion signatures, and then at the end inferring a peptidoform that accumulates all of this in one set of probabilities. And how is this done? Very generally speaking, in the first, we start with a certain library, for example, a library that we had from Shotgun, and then on this library, based on what we're interested in, for example, modification, we would create a new library that is that will generate a lot of query parameters, so a lot of possible localizations that we would like to consider. The next step is that we're going to try and do that detection step, so we're going to try to detect all the peak groups, associate them with a certain precursor that we think is the correct. So let's say this is a singly phosphorylated peptide and not a singly phosphorylated and oxidated peptide, and give a certain probability of that. And then we're going to do another set of rescoring in order to try and identify what is the correct site assignment by taking theoretical transitions and rescoring based on those. At the end, there's a statistical inference model that is based on Bayesian hierarchical model, and it takes all these sets of scores. So MS2 scores that are based on the MS1, MS2 scores that are based on the transitions, and then the transitions that we've added in order to correctly localize the site. And this gives us at the end a certain table with all the scores, and this of course can be using, for example, trick, as you've done in Turin, a line across samples. The result of this, which was nicely shown in the paper, is a much more full matrix. So the same peptides that were here queried with MaxQuant were then reanalyzed. It's the same data analyzed once by MaxQuant in DDA, once by DIA in IPF, and we get a much more full matrix that enables us, of course, more accurate quantification. If you would like to read more about this, all the details are in this publication. Are there any questions about this part? Good. In that case, I'd like to summarize what I've... So this is not we don't at the moment run it as an open search, so we don't consider all possible modifications. We consider all possible localizations on those modifications that you specify. So we still need, for example, to specify phosphorylation, and then take the unimode, and then take STY and oxidation. We need to decide which one are the localizations we're going to allow. Some people put it only on methionine, and others also on phenylalanine, and so on. but it doesn't run as an open search at the moment that considers all possible mass shifts. If that. Mm-hmm. Ah, okay. So, no. If I understood you correctly, you're asking if we had the phosphorylated, do we also then go and assign an identity to the oxidated phosphorylated, for example? So we look and we say this mass shift is allowed. And this we don't do unless it was originally included when we generated the assays. So if we permitted here to also have an oxidation, then that peak would also be assigned as an oxidated phosphorylated, and that peak would be assigned as a phosphorylated. I'll be happy to try and explain, but George is probably the expert.
So I think at the moment what he's doing is doing an open modification search usually in front, for example, in DDA. So it still requires a library, right? And so what he's been doing is doing open modification searches and then looking for what modifications are there and then refining this in the DIA data with this model.
But if I understood him correctly, he's asking if it's done in this step, and your answer is it's done in this step, right? Yeah. Where was I? So in this short talk, what I tried to highlight is a few considerations related to when we work with DIA data, related to the challenges and opportunities that come with this data. The first thing that we talked about is the need to do some transition refinement. So how you're going to select your targets, and this I don't go into, and how we select the transitions so far was usually by some top-end rule, although this morning we heard some interesting ideas on trying to refine the transitions in different ways based on the peak groups. But please consider carefully when you're pre-filtering your libraries or not pre-filtering your libraries that all identifications, including all site assignments, will make it into that library. And if you just choose them when you're, for example, importing in Skyline, then all of these will be, I would like to call them validated, but they're not really validated. We can very easily come into the case when we have two library IDs that point to the same chromatographic peak, and then we need to be very careful in how we deal with these site assignments. The second part that I wanted to highlight is the usefulness of RT information. This is not the case for every phosphorylated peptide, and I cannot tell you a lot about other modifications, but we certainly see that phosphorylated peptides that are modified on different residues will have shifts in retention times, and this information can be incorporated into your library and can be very, very useful. Whenever it's possible, what makes life the most easy is to have synthetic peptides, because then we have a ground truth and we don't have any problems, except for the part of using the PIs for quantifications. But then whenever we dive into DIA SWATH type of data, we need to start thinking how are we going to resolve the discrepancies between the number of IDs that we have, the number of peak groups that we see in the data, and the number of PeptidoForms that we need to consider. In some of the cases, and I've shown you today, something was not in our library, but we still found a very good peak group. So of course, all the scores that we're going to be using are going to be extremely helpful in trying to resolve this. Otherwise, we'll need to extract and re-extract manually in order to really figure these out. And I've quickly mentioned one tool that came out of this lab very recently that provides the statistical inference of the PeptidoForms so that you can try and resolve these modified peptides. And with that, if you have any more questions, let me know. Otherwise, I'd like to acknowledge all the people on the slide.
So any questions for Ariel about phosphopeptides? Bernd.
So if I got it right, you showed once a peptide that had actually 5 cysteine residues in, but only 3 had been assigned for phosphopeptides. So this is because you had this only in your library. You found only in the library these 3 phosphosites phosphorylated. Otherwise, you would have also to check for all the remaining 2.
Yes, that is very correct. So what you're alluding to is the fact that the site assignment from the shotgun would give us 2 localization and could be a 3rd. Is that what you mean? So there would be other possibilities on the sequence to consider except those that came out in the library. Whenever you do this manually, for example, or the synthetic peptides, then of course you, in that case, might consider all possible localizations. IPF considers all of them. So in the case that you have several possibly modified residues, it would take all possibilities into account as per specified. So you would need to specify that you would like to consider all serine, threonine, tyrosine, for example. You would not consider the alanine, for example.
Other question? Yeah.
So when you compared max quant to IPF, and you said it was less, you had more missing values there. Did you do the match between runs?
Yes. So for this comparison, was a lot of pain to get everything as closely as possible. So the library was built for MaxQuant. MaxQuant had the match between run options activated, and here we used the alignment using trick. And we tried to also control at the same level of FDR for the identification, so to keep them as close as possible, and then extracted, and then we took the peptides that are the same. So to give you as much as close as possible the real comparison, to say that. And the reason why we had so many columns, this is in the paper, is because one of the things that you see is that the more runs you add, the amount of missing values or degree of completeness have very different slopes. So you will start to add more and more missing values in alignment when quantification is done based on MS1 versus when it's done based on the MS2. And what the resulting heat map or the resulting quantitative table will look very different, and of course the power, your statistical power, and what comes out of all downstream analysis.
I mean, maybe it's worth saying that this is DDA data from triple TOF, right? Which is may not be completely optimal for MaxQuant, although they say it's so it's not only the comparison between the softwares, but it's also the comparison between the DDA and the DIA data, right? There's more than one sort of variable in there.
Good.
Okay, great. Thanks very much, Ariel. So what are we doing now, Betty? Straight into the tutorial, or? Yeah, let's go straight for the statistics tutorial, and we'll finish a little bit early today. Yeah. So let's take 5 minutes and then statistics tutorial. Start.